Hello, my name is Hayley. I'm a software engineer at Meta working in DC optimization. Together with Richard, we will be introducing Flux, a system for global capacity management. We recently published our work in OSDI, so if you're interested in learning more after this talk, I highly recommend you take a look at the paper. Flux was briefly introduced at last year's At Scale, and today we'll be diving deeper into the details of how it works. Let me first reintroduce the problem. So Meta currently operates at over 20 data centers around the world. But the existing capacity management systems operated at the region level, and as a result, service owners tend to reason about their capacity at a per-region basis. This, of course, leads to some inefficiencies. For instance, we have capacity imbalances. Our infrastructure promises to be resilient if any one region fails. We do this by setting aside disaster readiness buffers and distribute it across the regions. Capacity imbalances mean that we need to allocate even larger buffers since we must have enough buffer for the potential loss of the single largest region. Additionally, hardware utilization becomes imbalanced as some regions may have more capacity of certain types than others. Hardware ordering is overly constrained by specific services requesting specific types of hardware to be placed in specific regions. This becomes a compounding problem of heterogeneous hardware mixes across regions. Finally, services in mature regions have little to no room for growth, since these regions are already maxed out in terms of space and power. So we have this problem of regionalization. How should service capacity be apportioned across a large number of geo-distributed regions? Our problem must work on the scale of thousands of services in upwards of 20 regions. We have to consider the heterogeneous hardware mixture, even better if our solution can work towards homogenizing the regions. And we have to tackle the issue of complex service dependency graphs. Changing the capacity of one service can have a cascading effect and require that we resize it several downstream dependencies. Before, redistribution across regions involved complex negotiations between service owners and capacity planners. This was a very manual and tedious process, and because of that, it was limited to only a couple regions or a couple services at a time. As we continue to grow in the number of regions, this clearly becomes an unsustainable solution. So we introduce Flux. Flux comprises of three main parts. First, we use RPC tracing to identify a model that predicts service capacity demands given a traffic mixture for our products. We then use a mixed integer programming problem to jointly distribute service capacity and product traffic across regions. Finally, we have a capacity orchestrator that works with our existing auto-scaling and traffic management systems to safely and efficiently execute global capacity redistribution plans. Now, to dive into this first part, I hand it off to Richard.
Thanks, Hayley. I'm now going to dive into the first aspect of Flux, or our service modeling based off RPC tracing infrastructure. Service modeling is really important because we need to understand where the demand to our services is coming from. So at Facebook or Meta, we have regional decision points or routing decision points that we call products. So these products make an active decision to route a request from region A to B. And when that request enters that region, we expect it to stay in region or create an in-region dependency chain where we then need to scale the capacity up or down based off the demand from that routing decision point or product. So let's take a look at an example. Here we have two products, Facebook and Instagram, and only 5 backend services supporting them. This is a vastly simplified example, given that we have tens of products and thousands of services, and commonly a lot of these requests will make 10 to 15 hops in our regions. So here, though, we look at the Facebook demand. Facebook will make a decision to send a request to frontend 1 in either region A or region B. That request will then call feed and then indexing. So we knew that frontend 1, feed, and indexing are a dependency chain that needs to scale up and down with the Facebook demand. But this gets a lot more complicated because a lot of our products or services support multiple products. So Instagram will call into frontend 2, but those requests will also route into frontend 1, feed, and indexing. So when we look at the capacity requirements for indexing, we have to take into account how much of that is serving Facebook versus Instagram. And this becomes difficult because these requests do take multiple hops in our in-region. Like we understand who called us, but we have no idea who called them. So without giving a transitive perspective, it's really hard to scale and understand where this demand is truly coming. But let's take an example here. So our service model, or the true output of this model, is what percentage of my capacity is supporting a specific product. So in region A, we see that indexing is supported, is driven 40% by Facebook and 60% by Instagram. In region B, it's 30% by Facebook and 70% by Instagram. These ratios allow us to understand how much we need to scale if we move away demand. So in an extreme example, let's say we take all of Facebook and route it away from region A and to region B. We know that we need to downsize indexing by 40% as an example. So it gives us a sense of how much capacity is truly being used by a specific product. But as I mentioned, this is hard to collect because a lot of these hops or calls make multiple hops within our regions. But this is where RPC tracing really comes in handy. So at Meta, we use the capacity tracing platform where we basically add tracing code to specific services or our POPs in the Flux example. And when a request crosses this tracing code, we flip a coin and universally randomly sample. So we try to get a perspective of all of the demand in our fleet. If this sampling lands true, we create a tracing context. And this tracing context, in a nutshell, is just an ID that we add to the header. As this request propagates through our infrastructure, we check for the existence of this header, and if found, we create a data blob that uses CPU profilers, understands what service it is, collects service attributes, and basically creates a packet of what happened in that service for that request. So here, these are marked by the blue dots. As the request continues into our backend, we also check for the header and individual blobs representing each service call are created and then emitted to the backend. The tracing infrastructure then takes all of these individual events and stitches them together using ID correlation and timestamp values to create a representation of the entire request tree in an object. We then take those objects and process them through stream processing pipelines, extract all the values that we actually care about, and output them into our relational databases. So this is how we collect raw trace data, and this is really the foundation for how we understand our regional routing decision patterns. But we can't just use trace data. So one of the biggest challenges with tracing is that we don't have 100% of coverage in our fleet. So we have to take some steps to fill in those gaps. But our first step is using that trace data and understanding what product led to the demand in that service that we did capture. Our second step is understanding how much demand to that service are we missing. And then our third step is to fill in that gap with an estimate from the service owner themselves. So let's go through this example a little deeper. So in step one, we try to say what product led to this service call. So our data set right now has an individual row for every branch in the request tree. So you can imagine there's multiple rows with the same like trace ID and a row for service stack where we'll incrementally add another service as the row represents the request as it goes. But this leads to a two-step process. First, we want to understand what was the initial routing decision that was made for that request. So from our points of presence, we make a decision to send a request from region A to region B or region C. And that is determined based off a routing flag that we have captured in the trace. So here in the case statement, we can see that the source is POP and the routing was either FB regional or IG regional. This will determine whether we say it came from the Instagram or Facebook product. But the second step is understanding whether that request crossed a routing decision boundary. So there are certain services in our infrastructure that do handle their own global routing. A good example of this is the async infrastructure, where requests can be put into a queue and then dequeued and executed in any region. So that boundary of queuing basically identifies a boundary in our regionalization. So what we do here is we look at the service stack or the path that a request took and reclassify to the highest upstream service that identifies a routing decision point. So here we have a request that started in FB, went into foobar. The call into foobar would still be classified as an FB product. But as soon as we call into async, we start reclassifying. So the call to async and the call to BizBash here would be marked the async product. So that completes step one. With our real dynamic data, what is the accurate or measurable product demand that we see? Step two is identifying the gap in this data. When services want to understand their usage or their demand, they can use individual or internal service counters and get a really low latency, low sample like representation of what they're doing. But they have no idea where that demand came from. So that's where we try to use tracing to kind of consolidate it. In this example, in the first column, we see that trace data captured 60 calls to our service. But if we look at the internal counters of that service, we see that there were 70 in total. What we do then is identify the gap and mark it unknown. So 10 of these calls we're going to call unknown and really solidify the ratio of demand that we did see from Instagram or Facebook. But we want to get we want 100% understanding of the demand. So what we do then is ask the service owner, what's your best guess for where your demand is coming from? And with that best guess, we scale or fill in the unknown. So in this first pie, we can see the live trace data in an example where 50% of the demand is actually uncovered, and we don't really have accurate product attribution for it. So we go to the service owner and we ask, where do you think your demand is coming from? And they give a rough guess of saying it's basically 100% Facebook. So we get 100% FB blue in the static provided ratio. We then take that ratio and fill in the unknown so that we get a pie that represents 100% of demand with valid product ID attribution. So here now we see that 3% is Instagram and the rest we're going to mark FB blue. This is going to be the final output of the demand model for this service. But the real output of our service model is a capacity-driven model. So we take these product ratios and we break up the peak resource used by that service and then output raw metrics. Instead of saying 30% FB, 70% IG, we say this amount of physical capacity was driven by FB and this other amount of physical capacity was driven by FB blue or Instagram. And this allows us to stay in the units of our capacity planning. So that's the final output of our service model. Hayley's now going to dive into how we use that model in our solver to accurately place the capacity or do the capacity estimations.
Thanks, Richard. So the service placement model is a variation of the classic resource assignment problem. This model is distinct in that it jointly, simultaneously redistributes both service capacity and product traffic. First, let me introduce some notation. We have a couple assignment variables. First, capacity. This denotes the amount of capacity of hardware type H allocated for service S in region R. Next, we have our traffic distribution variable. This denotes the percentage of traffic for product P in region R. At the core of the model, we have the attribution ratio. As Richard mentioned earlier, this ratio is a product of peak capacity times the proportion of service capacity attributed to that product traffic. In other words, this estimates the amount of a service's capacity that is attributed to serving a specific product's traffic. So now for the formulation. This first constraint is pretty simple. It's just setting up the resource assignment problem. This is just saying the total capacity available is equal to the sum of assigned capacity for all services plus the spares left over. Next, we have our main constraint. This equation is saying that the capacity we allocate to a service in a region must be greater than the capacity needed to serve the proportion of traffic assigned to that region, summed up over all product traffic. This constraint is what defines the relationship between service capacity and product traffic that allows the solver to jointly distribute them according to our needs. So note that using the product attribution ratio, we're making the assumption that services are balanced according to existing demand. Since this is not necessarily true in practice, we add an additional residual variable to account for this and for any nonlinearities not captured in the model. We also use this model to plan for a service's growth. This saves us from manual planning and ensures that sufficient capacity is available in regions where growth is needed. Using linear programming, we are able to programmatically state our constraints and objectives, and this lets the solver make trade-offs according to whatever priorities are given by the user. For instance, we would like to balance spares across regions to reduce hardware stranding. We also want to minimize traffic redistribution and similarly reduce churn between future placement plans. And going back to our concern about the disaster readiness buffers, we want to minimize the size of a region with the largest capacity allocation. Some other goals include reducing deviation from the service model and allocating different types of growth, such as organic growth that's more dependent on the traffic distribution, or inorganic growth that is more dependent on product launches and therefore the capacity only needs to be given to certain services. If you're interested in the details of how we formulate any of these constraints, these are all listed in the appendix of our paper. Now I'm going to talk about the planning cycle process. Generating a plan is an iterative process that allows for step-by-step validation and human-in-the-loop operation. The inputs are given to the solver, which generates a placement plan. This plan is then validated by both service owners and capacity planners. If rejected, we update the model with any additional constraints and regenerate this plan. We can continue this cycle as much as needed until its plan is accepted by everyone. Once accepted, we have a couple additional overrides, either those made by a capacity estimator, which corrects for nonlinearities, or any manual overrides by a capacity planner. Our accepted plan is then passed on to the execution team. Overall, planning takes about 5 business days. In execution, our plan is converted into a series of steps. grouped into three categories: capacity upsize, traffic shift, and capacity downsize. In this diagram, we can see in the initial state of two regions with some available supply in region B. Say, for example, our plan shifts traffic from region A to region B for a more even distribution. First step is to upsize region B, allocating the available spares. Next, we redirect a portion of traffic to region B. And finally, we downsize region A, releasing capacity, returning this to spare supplies. The capacity orchestrator uses existing resource management, traffic management, and auto-scaling systems. Like planning, each step involves validation with the option of additional manual intervention. Overall, this process takes about 10 business days. And now I'll hand it back to Richard, or he will walk us through an example.
Thanks, Hayley. Now we understand what the input to Flux is with our service model and how the solver accurately plans for our capacity needs. Let's take a look at some solid use cases that use this system. So first is a very basic example of just regional utilization balancing. So now that we understand how much capacity is needed to serve a specific product, we can route and kind of rebalance the capacity needs across our regions. And second, a little bit more of an interesting use case that we have is hardware refresh. So a server can only live so long. And once that time comes, we need to basically replace it with a new server. But in order to do that, we need to unplug it. And when we unplug it, it can't be really serving requests from specific or any product, right? It needs to be idle so that we're not dropping requests or anything like that. So what we need to do then is understand how much of a specific product, or what we get is multiple levers, right? We don't have to route specific products away. But if we need specific hardware to be freed up, we know that we can pull a couple of levers. In this example, if we need to free up all of the hardware ones or half the hardware ones in region A, we know that we can either route Instagram away by a certain percentage or Facebook away by another percentage, and this will free up that capacity. And once those machines aren't serving requests, we can unplug them and replace them with new hardware. So those are some use cases that we have functioning today utilizing Flux. Flux has been running for about 2.5 years and serving thousands of our services. So let's talk about some more of the general things it's providing as well. So first, it rebalances service capacity to meet our infrastructure goals. So this is that idea of utilization, spreading out our capacity needs across our regions. Two is it distributes service growth capacity. By being able to understand how much capacity a service needs to support a specific product, we then can model how much it'll need to grow to support that product growth as well. And third, it manages projected regional capacity deficits. So this is an example that we just went through with hardware refresh. So if we don't have enough capacity in a specific region, we know how much we need to route back to it. Fourth, elevates our capacity management from a regional to a global problem. Historically, a lot of capacity placement or service sizing is done in like a regional bubble or a regional perspective. But with the fluidity of our demand and our capacity placement, we can now expand that to be a global problem. So instead of where do I need capacity in this region, we can say which region actually gets that capacity. And fifth is it decouples our global service placement from our global hardware ordering. So instead of saying that this service needs to grow this much in this region, we can just say this service needs to grow this much in general, and we can order that hardware to any region across our fleet. And this gives us a lot more flexibility in terms of where we can grow or where capacity needs need to be met. So Flux, those are some of the main benefits, but let's think about two of the high-level thinking. So Flux, or what is it changing, right? So Flux first is changing our contracts that we build with our services. So we're basically saying that you get low cost capacity, but you don't get to choose in what region you get it. And you have to be willing to accept that. And two is it allows us to think about capacity placement, not just in a one life cycle perspective. We can use this model to project multiple steps into the future and reduce the churn into our capacity planning. So those are some of the highlights and cool features of Flux. There's a bunch more and we can dive into them, but thank you for spending the time to hear us out and participate in our talk. Thank you.